Hello, good morning to all of you. Let me know if anybody has any doubts about how to submit assignment. Please ask me. And deadline is 27th. 27th afternoon, I'll be available in my office. And before, if you want to submit, you should text me whether I'm in the department or not. Uh, because I'm not available in all the time in my office. Okay.
हेलो.
Anybody has any doubts?
यस सर.
हाँ.
हम दिक्कत ये है कि कैंपस में हम रह नहीं रहे हैं, तो फिर वो दिक्कत होगी वो सबमिट करने में. तो कुछ ईमेल वेल प्रोवाइड करते जिससे हम सबमिट कर सकते थे.
This you are not attending practical classes.
नो सर.
Okay, so you write me email to me that you are not attending the classes. हमने आपको लास्ट क्लास जब असाइनमेंट दिया था, आप क्लास में थे?
यस सर.
तो क्लास में कोई ईमेल एड्रेस नहीं बताया?
नहीं, ईमेल एड्रेस तो नहीं
आप
बताया.
एग्जाम दिया था?
यस सर.
आपको नहीं मालूम है? हाँ, तो एग्जाम जिस एड्रेस
वही
में दिया
बात.
था उसी एड्रेस में पहले लेटर लिख. हाँ, पहले
अच्छा.
लेटर लिखिए कि आई एम दिस रीजन, आई एम नॉट अटेंडिंग लैब क्लासेस, आई एम नॉट इन द कैंपस. तो उसको आपको डॉक्यूमेंटेड होना है, ठीक है ना?
I am also
यू शुड
Satvinder
राइट ए
Kumar.
लेटर. ओके. Those who are not in the campus, please inform me in the first, write a letter, email that I am not in the campus. Give me permission for submitting online copies of that. It can be permitted, no problem. But you have to inform me what is the reason you are not attending the classes, lab classes. This is offline class, right? And then you should send your soft copy. Then only your soft copy will be accepted. And soft copy you can send in the same email address with the subject line your roll number and also the assignment. Everybody is supposed to write the question asked to that group. Okay, you should not attempt other question, and also you write your roll number as well as the questions carefully. You should quote the question also, not only the number. This is the question in the assignment sheet. And also for your sessional marks, whatever attendance, I have taken few days attendance, and attendance on regularities, performance in the class, all these also will matter for your sessional marks. Because all these are sessional marks by definition. Okay, so let us continue with the thing we were teaching. This is second last class. Saturday I'll take the last class. I'll finish your syllabus. So I was discussing that looking at the effective potential, let me write u effective, you wrote, is that the potential, whatever potential you have. For example, we were discussing the Kepler's problem. So Kepler's problem was minus alpha by r, alpha greater than 0, and plus what was that, L square 2m r square, right? L square by yeah, so here we draw L square by 2 mu r square. Yeah, so L square by 2 mu r square. So this is your effective potential, and we draw the potential. How to draw that I also mentioned. First you draw this, how draw this, then you should see at 0 and infinity the behavior, and from there you should able to draw the effective potential. So in this curve, this effective potential will be. Now, depending on the energy, suppose your energy is here. So, first case U greater than E greater than 0 and like say, so let me write U1. First case means U1. So, the particle in this region, so and then corresponding say R1, okay. So, this is if you draw the perpendicular from this point to this axis, it is R1. So, now if your particle's position R is less than R1, that means in this side, what happened? Potential is higher, so kinetic energy has to be negative, so that is not possible. So, this region is forbidden. You understand? Now, if R greater than R1, this side, if the particle, so this side is forbidden. Now, if the particle is this side, so you can see a open and particle will go to infinity, because this is the turning point. Particle will come here, here kinetic energy will be 0 at the meeting point. So, in this point that energy cuts the potential energy curve, that is the kinetic energy 0. So, particle will have only one turning point, so it will turn back. So only one turning point, and the particle will go back to infinity. Okay. So, this is E greater than 0. Now, there is a possibility that energy is negative and such, cutting in two places. So, now second case is E2, which is less than 0, and it is cutting in two places. So, let me write those. This is R2 and this is R3. Now, what happened if R is less than R2, that means this side, the left side of this graph. So, R is less than, potential energy is higher. So, again this is forbidden. So, let me put a cross, it is not allowed. If it is R is greater than R2, both, that beyond this region, again potential energy is higher. So, kinetic energy has to be negative, which is not possible. So, particle, this is also forbidden. So, this is forbidden. So, only possibility that particle R can be greater or equal to R1 and greater or equal to, less or equal to R2. Okay. So, this, in this case, what will happen, that it will be closed motion. Okay. That means particle will be confined to particle will be confined within R1 between R2, and that doesn't means the so particle will be confined between R1 2 and R2. No, sorry. This is R2 and R3 I wrote. No, this is R2, this is R3, this is R3. Make a correction, and this is R2, this is R3. Okay. So, particle will between R2 and R3, but this does not mean that your motion will be closed. So, this does not mean orbit will be closed. What I am saying, particle, see, suppose this is your bigger R3 and this is your smaller, say R2. Particle will be in this region. So, particle can go from here, take a turn and then come here, kind of thing, right, and go here. So, it may not be close, it can move. I cannot draw proper picture, but you can see in the book there is good picture, that particle will be, only thing is that particle will be in this annual region between R2 and R3. But of course, there is another possibility. Does not mean that will be closed always. Of course, particle can move in a ellipse also. Then if it is semi, this will be R3 and this will be your R2, semi major and semi minor axis. So this, but ellipse is also possible. So ellipse is also possible because ellipse has this R2 and R3 through radius, and then it can have a possibility. So, but which case it will be ellipse? For example, Kepler's problem, we know in this particular case it will be ellipse, but it is not always guaranteed that it will be ellipse. So there, depending on the potential structure of the potential, it will be. Okay, then third possibility. So case 1, case 2, and there is a third possibility. It is a negative energy, but it is equal to the minima of the potential. So third possibility, third case, E3 is less than 0 and E3 is equal to U effective minima. Okay. So now in this case, how many?
Sir, is it possible that a particle move between R2 and R3 and never retrace its path? Just it is bounded between R2 and R3.
Yeah, it's possible. It never will come back to the same point. It is possible. Only this analysis says only that it has two turning point. One turning point is at R2 and another turning point is R3. So if I have, so here it will turn, again it will turn in R3, then again it will turn at R1, R2, then R3, then, and it will without closing circuit. So if it cuts its circuit, or if it is it reaches, then it will be a closed circuit, right? But it is possible that it will never come back to its earlier position. This says only that you have two turning points. This is your R2 turning point, so you will take a turn, you will take a turn, you will take a turn, you will take a turn. This is always possible.
Okay, sir.
Yeah, but it's also possible, depending on the energy and this particular problem, it is also possible, if it is the ellipse also, then it is also possible that it can be ellipse. So both possibilities are there. Now in this case, so in this case, how many turning points are there? This case only one turning point. Case 2, there are two turning points. Now case 3, how many turning points are there? 1. How many turning points are there? Any answer? Actually, according to diagram, it looks like one turning point, but it is not. It has infinitely many turning points. It has infinitely many turning points, and all are at, say, R. So this, if this is the, suppose this is your R0, let me write R0. So infinitely many turnings. At R equal to R0. So in the third case, this particle will move in a circle. Circle is the only thing which circle has a radius. So this is R0 and it is always turning. So this circle, so this has the turning point. So from looking at the effective potential, you can always analyze your qualitatively. You can always analyze your structure. Okay. So, for suppose you have in case of Coulomb's in case of Kepler's problem you already have studied. You know that if your E1 greater than 0, then it is a hyperbola. If your E2 is equal to 0, that we have not considered in this diagram. If equal to 0, then it is again one turning point. I have not considered because this is always negative. This is always negative and going to 0. So this for E2 equal to 0, this will be parabola, only one turning point. Okay, and then if you have E3 equal to 0, all these are for Kepler's problem. E3 equal to less than 0, E3, E2, forget about my earlier notation, E2 equal to, so energy equal to 0, energy, let me write energy greater than 0, energy less than 0, then it will be ellipse. In this case of when this potential is minus alpha by r, that is Kepler's problem. So in that case, it will be ellipse, that we know, and then when if E is equal to U effective minimum, then it will be that ellipse will convert to circle. So ellipse, it is again a ellipse, but with the semi major and semi minor axis is same, so that is circle. That also you can understand from here. You just go lowering your energy, so your R2 and R3 will be closer, and they will become equal at this point. Okay, so that is the. Okay, so this will solve this problem, Kepler's problem, explicitly later, and we'll see that these things, and you have already done. My feeling is that, but we'll see at the end in the Saturday's class maybe, if we cannot cover. Suppose now if I give you a potential, so another problem to analyze through U effective. So another problem, suppose I say that U R is say minus alpha by r to the power 3, alpha greater than 0. This is not Kepler's problem, but another central force problem. So now your U effective will be minus alpha RQ, then L square 2 mu R square. So earlier it was R, now it is RQ. So nature of the graph will change. So first thing you have to do, you have to draw this curve, U effective, and how you'll draw the curve, because you can say, sir, I don't have graph paper, I don't have this, don't have that. How you draw? You have to draw a schematic diagram. So that I told you earlier also. So this potential is 1 over r square and can never be negative. So this 1 over r square graph will be like this. It will be very high value to and gradually go to 0, r going to 0. Now alpha greater than 0, it is RQ. So it will start from negative side. When r equal to very small, it will be very large negative quantity. So it will start from here. Okay. And then it will go like this. Okay. Going to 0. So now what will be the effective curve of these two? For that you have to decide that at 0, at r going to 0, which is dominating? R going to 0, this will be dominating. This will go to infinity faster because it is r to the power 3. This is r to the power 2. So RQ will go faster than r square. When r going to 0, it will go to infinity that faster, right? So actual curve will start from the negative side. This we understand. Now you can find a maxima of this, and if you do this mathematics, you will find there will be a maxima. then whether it will cross again and come in the negative side, that you have to decide when r going to infinity. So r going to infinity, r square will be increasing slower than rq. So going to infinity will be so this will be faster. Going to infinity, this will be faster. No, sorry. Let me give the analysis.
Positive side will be
No,
there.
not going to infinity, going to 0. So that I'm saying. Yeah. So what happened that are going to very large, you will have this function 1 over r square going to 0, and also this is and minus 1 over rq also will go to 0. So, but which one will go to 0 faster?
Sir, 1 upon r cube.
Yeah. So, this will go to 0 faster. That means at any instant of time, its value will be small compared to 1 over r square value, right?
Yes,
1
sir.
over, yeah. So, that is why positive will be dominating. This will go to 0 faster. That means it will be smaller. Always at the same point, it will be always smaller than this. So, negative will be smaller than positive. So, your graph. So, this is the procedure of analysis. You have to consider in 3 points: r going to 0 point, r going to infinity point, and r and maxima. Where will be the maxima? Whether maxima is positive side or negative side, that you have to find. So, if finding these 3 points, you can draw a schematic, not absolutely correct graph, but so in exam generally we ask this type of question. We give some potential and ask you to analyze the orbits. So then you have to consider, suppose my energy is here, or suppose my energy is here, or suppose my energy is here, or maybe here, cutting in 2 places. So these are the point you have to consider and analyze the exactly how I did for the earlier case. Okay. So I'll not do this exercise all details for you, but you should do this. And you understand why I consider RQ, because earlier it was 1 over R, slower than less power than this. Now we have more power in the negative side. So what will happen? So that is why I choose this. Now suppose another problem, you have U equal to say k r square. This is simple harmonic oscillator type of potential, right? This potential is like in the this kind of potential, right? So this is also a central force problem. And what will be the curve that you have to decide? So U effective will be half k r square. This k is positive, k greater than 0. Okay, so half k square plus L square to mu r square. So this will be your effective potential. This L square, this orbital, this angular momentum coming from the angular momentum conservation part always there, will be add up to the potential. So now you have to draw this curve. So this is your harmonic oscillator curve, half k positive side I am, and this is your 1 over r square curve. Okay, so this is your k r square curve. This is your L square by 2 mu r square curve. So how the curve looks like? So at r going to 0, what will be the value? Anybody?
Sir, tends to infinity.
So it will start from infinity. Good. Then r going to infinity, what will be the value?
Infinity.
again it will come from the going to infinity. So there must be some minima value. So you calculate that minima of this, minima or maxima I have to calculate. So your graph will be for this curve will be like this. Okay, so U effective versus R. Now, interesting thing is that in simple harmonic oscillator, in quantum mechanics, what we know, there will be a ground state energy. So this you can think of that it has some 0 point energy, which is like ground state energy, and any positive energy apart from the ground state energy will always have a bound state. So you can find any positive energy, so higher and higher positive energy. So what will happen? So let us consider the energy greater than this energy. It will have two turning point. This is R1, this is R2. Now let us see whether particle can have in this region. What will happen in this region? In this region, beyond less than R1, this potential energy is increasing. So kinetic energy has to be negative. So this is forbidden region. Now R greater than R2, this region, this side, right side of this curve. What happened? Again, this is positive, so kinetic energy, this is forbidden. So R1 greater than R2, so particle is always inside the curve. Particle is always inside the curve between these two turning points. So this is called the bound state. This kind of bound, particle is bound in this potential. So any higher and higher, because since it is going to infinity, this going to infinity, whatever higher energy you will have, you will always will be bound. So in simple, in this case, simple harmonic potential, you will find whatever higher energy, you will always find bound state. Particle will be bound. And that also we know in quantum mechanics that in harmonic oscillator, simple harmonic oscillator, quantum mechanics has infinitely many bound state. What are these bound state? You have you learned harmonic oscillator in quantum mechanics?
Yes, sir.
Yes, sir.
So this is the energy level n0, 1, 2, 3 to infinity. So whatever value of n, you will always get a energy level. So these are called the bound state solution. So exactly similar structure we can see classical mechanics by this analysis. So this effective potential analysis is very powerful. So any question? And also also you will find that this orbit of this particle will be ellipse, because there are two turning points with the different values. So in every energy higher than this energy, ground state energy, 0 point energy, whatever this minimum energy, you will always find the particle will move in a ellipse. That is two simple harmonic oscillator at right angles. You know mathematically, if you add two simple harmonic oscillator, you will get ellipse. So that it is always will be ellipse from our analysis. Okay, good. Any question? Now we'll move to another topic. Equation of orbit. So now we can understand qualitatively, not always with the very definitely. For example, in the first problem, we only know that particle will be between R1 and R2, but we don't know whether it will be open trajectory or a closed trajectory like ellipse. It may be open, it may be closed, even it is between R1 and R2. But we need to find the orbit equation. So once we find the orbit equation, then we will find that what will be the solution of the orbit equation will tell you exactly what is the orbit. So differential equation, so this is differential equation. So we'll find differential equation for orbit. So orbit. So the equation of motion, the Euler-Lagrangian equation of motion we have already calculated, right? If you remember, let me recall you, mu r square theta dot equal to L. This is the conservation of angular momentum, and then mu r double dot minus L square mu r cube equal to the force. So these are the two equations we have already obtained from the Lagrangian and then Euler-Lagrangian equation, right? But these equations are not the orbit equation, right? Orbit equation, this involves time derivative. Orbit equation means equation, so differential equation of orbit means equation of the coordinates only. That equation is called orbit equation. So for example, this x square plus y square equal to a square. So this involves the only coordinates and this gives the orbit equation. Or x square plus s square plus y square plus b square equal to 1. This is also give you the orbit equation. So basically, you know, these are the solution, means you get the information about the system, but we want to find a orbit equation. So to find the orbit equation, we have to write the differentiation in terms of theta. So r and theta, and we'll do this equation involving r and theta. So basically, you have to eliminate time. Eliminate time for this, from this equation, you will get the orbit equation. Okay. So let me write what will be the ddt. So because these are ddt, here there is a double derivative, means time derivative. So ddt and d2 dt square we have to eliminate. So I can write ddt as d theta dt times d theta, right? Now d theta dt, this is theta dot means d theta dt, so is L by m square. Mu r square. So this will be L by mu r square dd theta. So ddt I can substitute by this. Good. Now double derivative d2 dt square will be L by mu r square dd theta times L by mu r square dd theta. Right. Now this we can put in the second equation. Suppose this equation, if I put this equation, so mu, then you have r double dot. So in r double dot, let me write L mu r square dd theta, then L mu r square dd theta. This is your mu r double dot. So this dr d theta, r I wrote, minus L square mu r cube equal to f of r. So this will be the equation. So let us simplify this equation. So if this L is constant, you can take outside. So L, that is, this mu is also constant. So 2 mu, so L by mu r square, right? Times dd theta of 1 over r square dr d theta inside, and minus L square mu r cube equal to f r. Okay. So mu you can take out that side, r square. Okay. So now to further simplify this, we need to put r equal to we substitute 1 over r is as u, and this equation will be simpler. This is of course a orbit equation, because this involves only r and theta, no time. So this is orbit equation, but we want to simplify a little bit writing. So Excuse me. So this, we substitute this to make a nice equation. So you will have L u square. How u square? This 1 over r square is u square, and then you have mu dd theta, and mm, see this now if you find this, if you write du d theta, what will happen? Minus 1 over r square dr d theta. So 1 over r square dr d theta can be substituted by minus du d theta. So that is why we substitute 1 over r minus L square u cube mu, and then f of 1 over u, or f function of u you can write. Okay, so now this differentiation only one, so it will be minus L u square mu, this minus, so it will be d2 u d theta square L square, this is L square or L square, this side is L, no, this side also will be L square, right? This is L, so this is L square, I did mistake. So this is L square, this is also L square. So L square u square mu, if I take common, then it will be d2 d theta square, and this will be simply u, will be f of 1 by u. So I can write d2 u d theta square plus u equal to mu L square u square minus f of 1 over u. So this equation is very nicely written, and this is called the orbit equation. Orbit equation, this is small u, don't confuse with the potential. So potential is only in the f has the potential term, otherwise this small u is 1 over r. So this is orbit equation, differential equation for the orbit. Okay. Now sometimes orbit is given and you have to find the force law. So this is the problem also we asked many times in the exam, that orbit is given and you have to find the force law. So let us consider one example to illustrate this. Okay. So I consider an example. Suppose this problem, this is asked many times in exam also. Show that, or find the force law when force law when a mass m, point mass m, describe a circular orbit where a mass m moves in a circular orbit in the central force motion, circular orbit, and this orbit which passes through the origin. Origin of the coordinate system. That means if you have this circle is passing through the origin, this kind of circle. Any other geometry is possible, but this, so the particle central force motion, first is given that it is a central force motion, you have to find what kind of force will make the particle to move in a circle, but that circle will pass through the, that circumference pass through the center of the, okay. Origin is also center of the force. Origin means this origin is also the center of the force. So orbit is given, orbit is described. Now you have to find what is the f. So this so orbit is given means u is known. So only thing is that for this orbit what will be your u? So once you find the u, you will substitute in this and find your f. So this is the whole problem. So you have to find your u. So in such a case, this circumference passes through this. Generally equation is 2a is the radius, then a cos theta. So this is the equation of motion, equation of a circle passing through the circumference passing through the center where a is the radius. Then that means your u is 1 over 2a cos theta. So now you find your du d theta, you find your d2u d theta square from here, and you substitute back here, and you will get your fr. I am not doing this algebra for you. Fr will be proportional to r to the power minus 5. That means it is a central force, and that force is proportional to the r to the power minus 5, fifth power of the coordinate. So do this exercise, and there are many problems. Some of the problems, this is of course a problem given in your assignment probably. Okay, any question? And there are many other questions, so you, problems you can solve with this. Now I am going to tell you something about that. Tell me.
Sir, what is, sir, I didn't understand the meaning of origin as the center of force.
So do you understand center of force?
No, sir.
So that first you have to understand what is the center of force. Then if you understand center of force, then that is same as the origin. Origin you understand, right? Origin of the coordinate system. Okay. So when you have to consider, see, the central force is the f of r. So from where you are considering your r? See, just a minute, let me finish. So when you consider your two body problem, so initially I was here I was the radial vectors r1 and r2 we draw from this origin. Now after that, when we reduce it to center of mass and radial coordinate, we shift to this. So my center of force is shifted to here, because we are not looking at the whole motion, but we are looking at the motion with respect to this point, center of mass, with the radial coordinate. Or suppose you have a particle moving in a circle, so you have centrifugal force. So it should have a center, right? Where the when you write the force is proportional to Fr. So where from this R? This R from that, this now not this origin is the center of force. Here origin is here. Okay, and this is your new origin, and that is the center of force. So in this case, it is given that origin and center of force are same. So whatever that is why this equation is possible. R, this means that this is the R, this is the R, if I consider here. Okay. So I hope, but first you clear yourself that center of force, then you will understand. Any other question?
Sir, I have a doubt regarding the earlier topic that you told that in ellipse there are at two positions the direction is changing.
No, I said that if you have a two turning point at R1 and R2, then their motion, trajectory can be ellipse.
Sir,
So
like in circle there are infinitely many points, but similarly in ellipse the direction is changing continuously.
no, okay, turning. That turning, you can say that. Yeah, that you are true. That there also direction is changing continuously. But my statement should be that there is only one turning point. That means at one value, one or two turning point means one value of position vector it will turn. Now, if you motion is in circle, then position is always your r equal to r0. So always it will turn, right? So
Yes, sir.
and for ellipse, it is also always turn, and your okay. So that language, I can see the yeah.
Sir,
You have a valid question. Huh?
circle is just a special case of an ellipse.
Huh?
Sir, so both of them can be described in the same language, that the direction is also changing continuously in ellipse and circle too.
That is fine. That is no question of that. But now, yeah, okay. So what C is asking, Shruti is asking, is that why there are two turning point in the case of ellipse. So maybe I think source of confusion is that I should say for circle only one turning point. So let me reframe my statement. Only
Sir,
one turning point. Just let me finish. Then you'll ask. Only one turning point for circle, and for ellipse there are two turning point. Shruti, is that clear now? Then in that language, there is only one turning point where r equal to r0, it will turn. Ellipse, when r equal to r1, in my language r2, or r equal to r3, it will turn. These are the only two turning points.
Sir, only one turning point, then it won't come back in the same. What I mean is,
No,
infinite was the
no.
right one, I think.
Uh, okay, so that confuse you again, that if there is only one turning point, then
Sir, is
uh,
turning point definition related to what I am thinking, the direction one?
yeah, change of its direction. Turning, it is when it becomes your potential kinetic energy becomes zero, and then you cannot. The other side is forbidden, so you have to turn. So that is the, and no other turning point. So you will not return back.
Yes, sir, that will be a linear type of motion.
Linear type of motion. But it is possible that, but it is just a terminology. Motion, what is happening, that we know. For in the case of ellipse, particle is supposed to be, particle position vector supposed to be r1, in my case r2, greater or equal to r3. This is for sure. So it can be in case of, okay, so in that also, if you are feel comfortable, in case of particle will have motion in between r2 and r3. But why turning sense I'm not
Like,
getting.
yes, sir, I am getting that in ellipse at the turning point, the component changes in the opposite direction. Like, first it was going, it is slightly varying in the between those two turning point, but after the turning point, the component, one component changes its direction.
No,
Sir,
but it is
perhaps
no, it is continuous, no. So that So in this, if you have, it is not allowed. See, it kind of increasing and then decreasing. So if you increasing and decreasing, see, suppose something is increasing, then it start decreasing. So in that sense, it is a turning point. So
Yes, sir.
yeah, so decreasing, then it's continuously decreasing up to this point. So decreasing and then it start increasing. Okay, so this is the
Sir,
lowest possible.
sir, can we say that the velocity, I mean the instantaneous velocity is perpendicular at the turning points to the radius vector?
That is true, but every point it is true, no? This
Sir,
point also it is true.
No, sir, it
sir,
will be tangential, not exactly perpendicular to the radius vector.
But
sir, I was thinking, are these two spaces equivalent? We were seeing these turning points for V effective, and now we are mixing that up with the orbit of the particle.
no, I didn't get your question.
Sir,
Question is that only question is the terminology. How will use the terminology? It is everything is clear. For a case of ellipse, there are, I said, two turning point. In case of circle, I said infinitely many turning point. So that leads a little bit confusion about the terminology and language. This is the only physics wise there is no problem at all. Tell me your question.
yes, sir, I was saying that when we saw these turning points, we were plotting V effective versus R.
Yes.
And now we are seeing that graph that is R versus theta.
Where is the graph? This is R, not R versus theta, no?
Sir, the graph of ellipse or of circle that we draw R versus theta.
Okay. So that you are right. Uh, yeah, you are right. Very good. So this maybe the confusion, source of confusion. Yeah, you are right. So the this turning point is that where you have U effective versus R. So there is a turning in the value of R, right? So if so now I think everything will be clear. So value of R, there is a turning, right? So when you have a ellipse, so you have a this, you reach a R2, this is maximum, then it start decreasing. So that is the turning. So you are going to increasing and then start decreasing. So that is actually turning. So there are actually two places at R equal to R2 and R equal to R3, there will be two turning. So in fact, if you look at this graph, it will, you can, those turning points, this turning point is, one is here, another is here. But you have to look at the, don't confuse with the graph with U effective versus R graph, because there you had the R. Okay. And here you have X and Y, right? Or R and theta, X and Y, you can think of. So that is why it looks like that it continuous turning, but that is not true. For the case of circle, it never changes, right? R equal to R0, it is always R equal to R0. So no, you can think of one not in as a either you think of infinite kind of turning, or it says no turning, right? It is a circular motion, it will circular. So no, it is not taking any turn. R is always fixed in that sense.
Yes, sir.
R is always fixed. So turning means that you have to look that value of R, position vector, magnitude, how it is changing. Okay, I think this issue is clear. The situation was clear. Next thing we want to study, but is not possible today, that stability of the circular orbit. So maybe that will conclude this Saturday. We'll have this, and then Kepler's problem. Little bit of Kepler's problem we'll discuss, not the integration, etc. will not carry out. So these are the two topics we'll discuss in Saturday class, and we'll have time for at least 20 to 30 minutes for discussion or revision, or you have any question in the whole class, because Saturday class will be the last class. Okay, so any question for today? Otherwise, we'll stop today's class. And practice your problems, uh, uh, solve problems, learn things, because your paper will be tough. I mean, not will. I mean, tough means not will be that straightforward. You'll get from the notes or some straightforward from the books. You'll write down the answer. You have to work out. Somebody has to work out. Then we copy each other. That is a different issue. But somebody has to work out. So if you take loosely your paper, you will not able to write all answer. But you have to be serious. Only unseen problem will try to give you only unseen problem, not in the assignment, not in the notes, not in the books. This kind of problem will try to give you in the exam. But those you can solve with your knowledge. So this is the idea. And I am noting every day or nowadays that who are the present. Okay, so maybe we'll stop the class.
Sir,
Huh.
sir, I have a question that the planets sometimes, sir, मतलब, sir, disturbs from their orbit after few years. Sir,
Huh.
is the reason that is there any reason that they have the
No.
potential?
Your statement was not complete. Planet moves in a elliptical orbit. Then
Yes,
what you
sir.
said? Then you
Sir,
said that
but
orbit
but they,
changes.
yes, sir.
Orbit changes.
Yes, sir.
So
After few
that,
years.
that I understand. So you are saying that there is a precision about the orbits. When after many years the orbit was not in the same orbit, right? That you are saying.
Yes, sir.
Yeah. So for those consideration, you have to consider additional things. We are simple model, Kepler's model we are studying, and we have to consider other things to get those precision. Those are very
And
negligible amount. Yes.
sir, as here we considered the potential energy, effective potential energy, that
Oh.
the body moves in R2 and sir, R1 and R2 orbit, two bound
No.
state.
R1 and R2, there are is position vectors, maximum and minimum value.
Yes, sir.
R1 and R2 is the position vectors, maximum and minimum value.
Yes, sir. That is two bound points.
Hmm.
And the planet moves in this bound state such that they turn like and follow elliptical path.
Hmm.
So their effective potential is such a function of r that after few years it changes its orbit, or any other approximation is considered.
No, your question is not clear. What I said that your whatever orbit it has, it will be so far whatever we consider your orbit will be same for all years. But there are additional concept you have to use. Those concept will tell you that this orbit or these values may change very small amount over the long time. And over the long time, when these values changes, R1 or R2 or whatever values, then your orbit also will be slightly shifted from the earlier one. And that shifting is very small. and from our this consideration you cannot get those corrections.
Okay, sir. Okay. Sir, I thought that this will be enough, sir. Whatever we
No, no,
studied.
no, no, no. See this orbit, see, we are not considering the exact situation, right? Suppose a planet is orbiting, so you are considering the force between sun and earth, right? Or the
Yes, sir.
planet and the sun, but that planet can have force due to another planet, that
Yes,
planet can
sir.
have force due to others, so you have to consider all possible type of corrections, then only you get the correction, right?
Yes, sir.
So if you consider only that force between the planet and sun, then you will not get the speciations.
Okay, sir.
Any other question?
Thank you, sir.
Okay, maybe I leave the class. Oh, I have to stop recording, no? Yeah.